All right, so let's begin. So what I want to cover are things that are in the book partially, but superficial. Some things that aren't, some things that Michelle and Suki touched, and I want to plunge deeper. And some notions that I think that are very important for us to understand better. So let's begin. Okay, first of all, let's talk about neuronal communication. So neurons are dumb. All we have are all our neurons. They are the same stuff. They follow the same. They have the same attributes. They are switches of yes or no. They are unidirectional, and they have, and everything in neuronal communication is a function of time. So we'll plunge a little bit on those notions. So you already know we have every neuron, we have a cell body, and then an axon that in the end releases chemical neurotransmitters into the synaptic cleft, which then activates the next neurons. So that's true for everything, including our receptors, including, so in vision, we have photoreceptors in the retina. So instead of the dendrites, they have a mechanism that is activated by electrophysiological, by electromagnetic waves energy. So they are attuned every time this specific kind of energy, we'll get there soon, you already know, then they fire. The same for taste. The first, instead of the cell body, instead of dendrites receiving input stimulation from other neurons, like all the neurons inside our body, from the muscles, all the efferent nerves, everything is the same. It receives input, either chemical within the body or physical for all the receptors, and they fire. So touch is mechanical, smell is chemical, taste is chemical, and hearing is mechanical also. Activated by sound, by waves of sound, by pressure of air touching them. All right. So the first thing that we want to remember is that neurons, they don't transmit information. There is no information embedded, intrinsic in neuronal activity. Information is our interpretation. Somewhere it happens there, that's the big question. But information is our interpretation. It's not what the system conveys from neuron to neuron, from system to system, from area to area. All they convey is electrical or chemical pulses. So there are two types of communication. Electrical, it's within the neuron itself, and chemical between the neurons. Neuron transmitters in the cleft that excitate the next one. These processes, the main variable is time. We'll get there. So within electrical communication, that is within the neuron, it works by diffusion and electrostatic pressure. So diffusion would be when you have a concentration of something in the same medium. So automatically the concentrated thing disperses along the confined area. Like smoke in a room, it will disperse. Even when you have a membrane that is partially permeable, those particles that can pass, they will diffuse as if there was no membrane, and those that cannot pass, they will not. Right. The other one is electrostatic attraction or repulsion, like any magnet, right? So within the neuron, as you already, even from introduction to psychology, you already learned that we have a lot of channels, and then specific things enter and go out. It depends again on the concentration, diffusion, and on their their magnetic attributes. They bind together with other things or they repel other things. So you may ask, or students usually ask, something that is usually not clear: how come it's unidirectional? If it's only by diffusion and magnetic attraction or repulsion, how come it doesn't go back? If here in the middle, well, these are myelin shells, so here there is no communication with outside, but in those small gaps in the myelin, then again, the action potential is renewed. So an axon can be, we have axons that go from the brain. I don't remember which one is the longest, but we have like, I think 2 feet of axons for some afferent nerves. Or in the cell body, how come if it's everything is floating and it goes everywhere with the diffusion and magnetic, how come it goes only in one direction? So it works, and it always works because it begins somewhere. So it works like a wave. And the wave only works because of time, because every little process that happens locally is followed by a period of time during which this process cannot occur again. And then whichever process it is, it may be mechanical, it may be chemical, it may be electrical. Every one of those mechanisms, they occur, yes or no, or none, and then they need time to reuptake, to recharge. During this time, nothing can happen. So that's why when it begins here, these guys that have already, something already occurred, after that moment here, nothing can occur again. So it naturally follows to the area, to the location, to the direction where these mechanisms haven't occurred yet. So there are many mechanisms, chemical, electrical, etc., but all of them are according to yes or no, and according to frequency. So during the reuptake, different mechanisms, they have different times to reuptake, and that, first of all, the direction, as I just said, and the second of all, the time, the range of frequency that process can occur. For a neuron, the frequency that it can fire. So there is a maximum rate that a neuron can fire from the resting potential. As you know, every neuron in our body is never totally quiet. So different neurons in different areas, in different moments, they have different resting potentials, which different frequencies, which means that every here and there they fire. Uh, and the difference is how is the a long time the changes in that frequency. So here is an example for one of these mechanisms on the membrane of any neuron. So immediately after the action potential, we have a refractory period in which nothing can happen. All right? We have different kinds of refractory periods for different parts of the neuron. In different neurons, it's different in different mechanisms, but all in all, there is a short period of time during which nothing can happen. It's recharging completely, it cannot fire. Then there is a semi-refractory period in which only a very strong stimulation can make it fire, and the normal refractory period in which it will fire if activated. And then we have the chemical communication, which is between neurons, which happens when in the end of the axon, in the axon terminals, different neurons release different neurotransmitters, different stuff, different chemicals, serotonin, norepinephrine, dopamine, etc., which even the same neurotransmitter can have different results in the next neuron. It can excitate, it can inhibit, depends on the connection. This is a very rudimentary mode of communication. It's diffusion. In the synaptic cleft, it's liquid and there is no direction. Nothing is organizing, nothing. It just releases it and it floats randomly. And some of them randomly cross the area into the dendrite of the closest neuron, and then it activates, which means that it's a function of concentration of different neurotransmitters in the cleft, which means that it also turns, the only difference ends up being frequency, time, release along time. So different neurons have different processes of reuptake, that is bringing back the neurotransmitters released in the cleft, which may inhibit the communication. So for instance, so I said caffeine before. So one of the reasons that when you drink a lot of caffeine, you have a high and then you have a lower than you were before, it's because the caffeine during the excitatory period causes many specific neurons in specific areas to release specific stuff in the intersynaptic cleft. And then the reaction of the same neuron or the entire environment is there is a high concentration of those excitatory neurotransmitters, so they end up absorbing back all the overhead. And if you have increase very fast, the reuptake is also very fast. That's what leads to the dip after the high. Methylphenidate, cocaine, which is the same thing. Adderall is methylphenidate with methamphetamine. But what they do is they bind to those reuptake mechanisms in the intersynaptic area between neurons in specific areas that are connected to emotional high attentiveness and many other things. So they bind to those specific transporters that bring back the dopamine to the previous neuron. So when they bind to those, the dopamine remains in the intersynaptic space, and they keep on exciting the next neuron. That's how it works. So here we have, this is a generic example. So here we have the neurotransmitters. They swim within the axon terminal. And then when the action potential arrives here, it does things to them, and they go and break out their vesicle, and the neurotransmitters are released here. And then some of them, let's see what's enzyme break. So sometimes there are enzymes that break those neurotransmitters. So the concentration of them in this area is a function of the amount of enzymes, the amount of those transporters that reuptake, that bring back, and the amount of channels in the next in the receiving neuron. Different areas have different mechanisms with different reuptake systems, different channels. Sometimes the dendrites, they themselves release enzymes that break them out, or a myriad of different mechanisms. But all in all, everything is about release, concentration, which determines frequency of excitation. So, all in one, yes or no, all or none is fire, not fire. Unidirectional, we understood. Temporal constraint, reuptake, and many other things. Frequency of fire is the only way to build, to achieve the endless patterns that somehow bring us to perceive, to feel, to be what we are. Because neurons are very simplistic devices, and they do nothing apart from fire, not fire. Okay. So we have, does anyone has any idea how many neurons we have in our body? You probably, maybe you've read, I think most textbooks, they have a estimated amount of, I don't know, I don't remember, billions or trillions. And it turns out that nobody knows how many neurons we have. Someone in Tel Aviv University many years ago decided to check where that number that all the textbooks have been repeating for I don't know how long. And this person discovered that it began some, I don't remember, maybe 30, 40, 50 years ago. Someone in a ridiculous calculation estimation based like total speculation, and it was published somewhere. And since then, nobody checked because I don't know. It's maybe, but nobody checked. And there is one number running for decades, and is based on one person out of speculation. So we don't know how much there is. But all this enormous amount of very simplistic devices, which can only differentiate what their activity in terms of frequency of firing. So they are behind everything, our life, our experience, our everything. So two mechanisms, two notions, two concepts that we assume to somehow explain the richness of what we are is sparseness and distribution. In this lecture and the next lecture, I want us to understand it better. So sparseness means that each stimulus is encoded by a strong activation of a relatively small set of neurons. That is, a piece of light? No. Light that reaches, light that has a meaning, an object, okay? An object that reaches my retina, upon which conveys all the information. I said there is no information, but the information that upon which any meaning my system can retrieve, can interpret, all this information by the end of the day is only a small number of neurons react to it. And then it converges to even smaller numbers and pass on. On the other hand, so how come this funnel of processes can reach, can explain, can account for everything? So the second process is distribution, that the same stimulus is correlated with very specific patterns across different areas. And areas, it doesn't matter. I don't want to enter areas because areas in the brain, neurocorrelates is, I don't want to enter metaphysics again with you, but let's forget about areas. It's a big question what it can explain to us. And sometimes it confuses more than it explains something. It explains many things, areas. But many people think, and I agree with them, that because it's so comfortable for us to talk about area, it ends up blinding us to ask better questions. Okay. So, but what is not restricted for explaining the endless possibilities that account for our experience is the idea of distribution. So, stimulus and light. I want to spend 2 minutes, or maybe more, explaining something about this story about light, because all the senses that we know, okay, taste, smell, particles of chemical stuff, touching, we understand. Touch, obvious. Hearing, sound, it's easy to understand, but light, which is probably the most important, or I don't know if it's the most important, but we feel that it's the most important sense, like vision. And in terms of, let's put it this way, research in perception is the biggest chunk. And yet the stimulus itself, this electromagnetic wave, is confusing for many students. So I want to spend a moment talking about it. So electromagnetic waves is energy. Is energy running through. I'm not a physicist. I cannot explain what exactly, how it works, and even if I could, I don't think I don't know if it matters. But what matters is it is energy that travels through space in the form of a wave. And this energy, whenever it has different wavelengths, so we can see here that, let me move to the next one. So this is light from the sun, white light that encompasses all the different wavelength. Wavelength is like the not the amplitude but the frequency. This is a very short wave, this is a long wave. Okay, so white light, light from the sun, encompasses all the different separate waves. So we have very short frequencies, 1 nanometer. These are gamma rays, X-rays, ultraviolet. Then we have this very short and restricted range of wavelengths that our cones and rods are sensitive to. And then there are other stuff. These straight lines here mean that these wavelength, they don't reach us here, animals on Earth, because of the atmosphere, which is a medium full of stuff, full of particles, air and other things, and gases in different areas, and they filter it, they bounce back they either absorb or bounce back those waves. So the waves that reach us are those that we humans see. Different animals, they have different ranges. I think most mammals, it's not too different from this area. Here we have something that reaches, I don't know what it is, and we have radio waves between short and long waves that they run freely through the atmosphere. That's how we can communicate through radio waves, including to space and back. Now, these waves of energy, when they bounce on something, they are either absorbed or bounced back. Let's say like this. How do we see colors? Colors don't exist. Colors are interpretations that we, inside us, it's a feeling, it's a qualia, that it's our interpretation of different length waves. Why do we and some other animals, many animals don't see colors, don't perceive colors, don't differentiate colors? Why, in which situations we find it useful for differentiating stuff around us, from things to eat to differentiate material? We it's a way for us to interpret different things around us. So how do we see colors? When a specific wavelength bounces on something whose pigment is commensurate to that wavelength, let's call red. So here we have the visible light. So red are the long waves within our range of visible light. So when something with the pigment red has a pigment red and a light that is either red or white bounces on it, if it's red, the red light bounces back. If it's white, only the red light bounces back. What happens to all the other waves? They are absorbed. And this absorption is the crux of how our cones and rods react to light. So how come a pigment, a specific pigment, absorbs only one light? So white light that has all the waves, only one of them is bounced back, and those that we can see. So imagine that everything, every physical thing, is, when you look inside very close, nothing is really solid. You already saw pictures of atoms, right? There are things, little quarks and things flying around. Everything is compressible. Again, I'm not a physicist, I cannot explain, but things, there is space between things, and different things react differently to this wavelength, to the energy in it. So imagine that this is a this is the best demonstration I could come up with. Imagine that this is tissue. Okay, this is molecules. They are close together. They can be compressed. Everything can be compressed, or they are in their natural, not natural, but wherever they are according to their concentration and everything. Okay, so let's say they are like this. So imagine that something very small, can you see from there? Something very small can go through this specific texture. Something very big would also go through. There is only a small range of things of size that will bounce back. Okay, so that's the idea of specific pigments reflecting very specific length of electromagnetic wave. So we have three kinds of cones, right? We have the red, blue, and green. Each one of them, they have a specific mechanism, a chemical thing, that when that specific wavelength reaches it, the energy within that wavelength, which is the same energy as any other wavelength, but the frequency is very specific. So when that energy with that frequency bounces on, reaches it, a chemical reaction, a chemical physical reaction occurs, and then that cone, that receptor, changes for a moment because of that energy absorbed, and it starts a chain process like every other neuron that it fires, etc. The rest we know. So each one of our four types of photoreceptors, they react to a different specific wavelength. What time is it? Okay, I have to run. I want... color doesn't exist is a... Does someone find it absolutely incomprehensible that I'm saying that color doesn't exist? that it's an interpretation that we use? No one, right? Sound doesn't exist. Sound, by the same token, is compression of air in a specific frequency a long time that reaches our ear, etc. Every information is an interpretation of things that we don't have access to it. We are mediated by these very simplistic mechanisms that are the receptors on the beginning of the chain of our perceptual system or of each of our senses, and they are sensitive to a very specific thing, and then they fire. But these again, it's a mediation. It's not what we perceive. I'll run with something that in my conversation with students, it's not clear to everybody, the visual field. Okay, first of all, so we have in the fovea, the fovea is an area in the retina. It has something 1.5 millimeters diameter. It's a very small area. It's our best, it's where we have the best resolution. We have a concentration of cones. I'll talk about more details in a moment. 20/20 vision occurs only in the fovea. In the best cases, for those of you that have 20/20 vision, it's only on that central area of the retina. 20/20 vision, just for you to know the classic thing, 20/20 means 20 feet, 6 meters. Okay, so if from 20 feet away you can read the letters, means that you see all right. So we have two eyes. Our two eyes are separate. It's two separate static pictures, cameras that take pictures of the two eyes. They are consolidated, they are combined, and they are interpreted so we perceive a three-dimensional experience of the world. We don't have access to it. Can people with one eye perceive depth, three-dimensional? Yes, of course. It's more difficult if someone loses an eye. There is a period of learning, but people that are born with only one, they can perceive 3D perfectly well, because we use a lot of convergent independent clues about that person. Occlusion, distance, size, our knowledge about what's supposed to be sized, many different things. There is in the book, I'm not going to cover it because these are simple stuff. Just read there, it's very well explained. And if you have doubts, talk to me. Okay, visual angle, what I wanted to say. The angle is the size of an object that reaches our retina. The angle is the translation of that size. So if you take half an angle is, let me translate here. A nickel, if you take a nickel and you put at arm's length, that will be more or less half an angle. And that will be more or less the size of the moon when you look at the moon. And so something the size of a nickel 2 feet away is identical, retina-wise, identical to something that double the size of a nickel 4 feet away. All right? It's 2D. It's the same angle, so it doesn't matter how far it is. That's why we need all the depth perception clues that we use. So we have two eyes. Each eye has something like 80 degrees of visual field. The two of them together, here it looks like 110, but it's more. Yeah, it's more like this, it's around 220 degrees. So if you stand your arms to the side and you move your fingers until you perceive some movement, you'll see that it's more than 180 degrees. The sun, again, oh, I said the moon, so the moon, oh yes, the moon is closer. So according to, maybe it's not accurate, but according to this, the size of the sun and the size of the moon in our retina is not too different, even though the sun is, I don't know how many times larger. The blind spot. Okay, wait. When you read papers, so one thing that you already know, that one of the information that must be conveyed in any scientific report of any kind is all the technical information, the methodological information, in order for others to replicate what you did, either to replicate as a control for a different manipulation, or, well, that's usually the case. But in order for any idea, for any hypothesis, any theory to be accepted, the observed effects, the observed events upon which an idea, a theoretical idea is based, must be replicable, okay? In order to replicate an experiment, a method, everything that concerns vision, distances are obviously extremely important. So usually you will find distances translated to degrees, visual degrees. So all the stimuli, this is an example, they were at 1 degree height. And in another place, it may or may not be explained the distance between the retina and the screen and the stimulus, but it doesn't matter, because the important thing is the size of the stimulus reaching the retina. So it can be 2 feet apart, and it will be probably something 1 degree in the normal distance from a screen will be something like 2 fingers, okay? This will be more or less 1 degree, I think. So maybe in a different lab, they are using a larger screen and it's further away for whichever reason, it's further away from the eye. What's important is is it clear? Anyone stops me if I'm not clear? Okay. Blind spot. I wanted to explain, but is there anyone that hasn't heard or doesn't know what's the blind spot? Chat. Okay, blind spot, very fast, is a specific area where all the bundles enter. It's here in this area. Okay, so here is the blind spot. This is a strengthening of the retina. Okay, so we have the epithelium, so the light comes from here, bounces back into our neuroreceptors, and then we have all the intermediate cells and the ganglion cells that they go in bundles towards the optic nerve. In this area, there are, because something needs to enter, there are no receptors. We don't see. We actually don't see. Our brain is all the time extrapolating from all the rest of the information reaching the retina and patching it. it's information that we don't perceive, that we don't see. It's being artificially, not artificially, it's being completed inside our head. So here is more or less the degree that we have our blind spot. This is a demonstration. You can do it at home afterwards. You close, put it as a full screen on your computer, close your left eye, and then if you get closer, okay, I am something like 40 inches from my screen and I cannot see the dot. It really works. Try at home later, okay? Right. Some important things that can explain a lot of things in perception, which are consequences from the differences between rods and cones. I'll jump to it. Michelle and Suki, they touched on most of them, not all of them. Superficially, I want to talk about what I think is the most important. How much time do I have? 15 minutes, right? Okay. All right. Distribution, you already know most of the cones are here in the center. We have cones everywhere, but they are few and they are evenly distributed everywhere outside the fovea and the parafovea. Our rods, they are mostly, we don't have rods in the fovea, and we have them distributed in all our peripheral retina, the peripheral visual field that that our retina receive light from. Okay, let me show you for a moment what I talked about before regarding time. That one of the every neuron, every version of neuron, the first and foremost thing, behavior it can do in order to build complex patterns that can end up being interpreted as complex information that our experience, endless rich experience is based on, is frequency, is firing a long time. So photoreceptors and every other neuron, once they fire, they stop firing, they need to recharge, reuptake. So this is a cone of a frog immediately after being flooded with light. So in the first moment, the chemical material that reacts to the specific and to the energy of that specific wavelength, when it reaches those chemical materials in the beginning, it reacts. This is a picture. This is immediately after being reached, being excitated by the specific stimulus, specific light, and then a long time it bleaches, meaning this is the chemical, those chemical sensitive particles that they start to be transformed and they become electricity that fires, that end up going through the axon and firing. A cone, each cone, one single cone, once it fired, once it has been bleached because we can see what happened, it becomes white. Well, it takes 6 minutes in order to recharge. A rod takes 30 minutes. How come we are all the time seeing without as if everything is It's like the cicadas. I just read today that we are waiting for billions of cicadas every 11 years. Every 70, they live 17 years under the the earth, and every 17 years they come, fly around, mate, go back to the underground for another 17 years. How come we have cicadas every year? Because different cicadas, they start and end at different times. So the same for rods and cones. At every given moment, we have only a small portion, a small percentage of cones that have just finished to reuptake, to recharge, and then they fire, and then they go again for 6 minutes to rest, the rods for 30 minutes. If suddenly we had all the rods and all the cones resting, let's say we are in the dark, what happens when we reach light? We are flooded. We cannot look. It physically hurts our eyes, right? It's because most of our photoreceptors, they were ready to fire. They were in the dark, and they fire at the same time, and there is an overstimulation of all the infrastructure, the neuronal, the retina, and everything. It literally hurts. Okay, distribution. So we have much more rods than cones. Okay. Now, this is important. Rods. Let me show you the picture here. So we have, these are our cones, the fat ones, and these are our rods. Okay. This is a schematic picture. If we have rods and cones together, so it's not in the fovea, we don't have rods in the fovea. I don't know if this is fidedignon to what happens in the peripheral, but let's say it is. So each cone, through this maze of mediating other cells, they end up connecting with a ganglion cell. Rods the same. This web of connections is like this. Rods, this is light, these are the rods, the photoreceptors, okay, light comes from here. Many rods, they end up, their axons end up, here we have again all the medium, the acromine, the horizontal, it doesn't matter. They end up how do you say it? They end up in one ganglion cell. Many rods in one ganglion cell. The cones, they have, well, here in the picture, one per ganglion cell. One per ganglion cell is only in the very center of the fovea. Most cones, they are connected to most cones, they are combined to more than one cone, like 2 to 1 ganglion cell, 3 to 1 ganglion cell, or in the best case, 1 per 1. What does it mean? If a ganglion cell needs a given amount of excitation in order to fire and to fire through the optic nerve, so let's go with these numbers here. So if it needs, let's say, 10 units of excitation, so light of 2 units, very little light, upon an area with 5 rods will cause it to fire. In the case of cones, we would need 10 in each one of those for this to fire, because the same light the same amount of light falling on the same area, so the stimulus has the same size, falling on the same area ends up not excitating any ganglion cell. So this amount of light, when it falls on the fovea, we don't see. It's not enough light. The same amount of light on our peripheral visual field, meaning on the periphery of the retina, on the same area, will fire. Which means that our peripheral vision is much more sensitive to light. We need much less light in order to perceive something when it falls on our periphery than when it falls on our fovea. Which also means that because the rods are bounded together, a co-op to one ganglion cell, a large area conveys the same information. So we have much less resolution in the periphery for the same area, for the same light. While in the cones, if indeed in the area that we have 1-to-1, we can differentiate between a very small area. Okay, I'll say it in different words. Let's say that the light falling here and the light falling here, they are two different objects. Because in the fovea, they excitate two different ganglion cells, we can, technically, it is possible for us to differentiate between these two stimuli. The same situation in the peripheral area. First of all, it's only these two, they will not excitate, but even if they do, we cannot differentiate between these two objects because they will render exactly the same neuronal activity through this ganglion cell. Okay, this is, if you at home do it afterwards, if you fixate on this X, you will see that you cannot see more than 2 or 3 letters. You will see all the letters, but your acuity falls very fast when it goes out, your resolution. This is a simulation of how we see. This is a two-way simulation. If you are looking, if your fovea is looking here, so the further away you have less resolution and you see less light. This is not a good simulation for a normal situation because our rods, they are more sensitive. So actually we wouldn't see darker. We maybe could we don't perceive it lighter because we correct for it, but the information that is passed by our rods is more light, more excitation. So this would be a more accurate simulation for dark adaptation, which I want to say fast. Okay, this is how dark. This is how this. Maybe you've seen it. This is the dark adaptation curve. This is the experiment, how it was. So it was done. So the participant is asked to fixate on a given point, and then a test light is presented on the periphery a long time. So so it begins with a normal lighting room, and then the lights are turned off, and then a test light is presented here, and the participant has a small knob that the participants can adjust the intensity of the light until it starts to perceive. So immediately after the light was turned off, the participant will have to increase the intensity of the light until here it sees, and during time it decreases, 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 decreases. Okay, and then we reach to this curve. What happens is like this. In the beginning, in the first 3 to 4 minutes, the sensitivity, from the moment the light was turned off, the sensitivity improves more or less. It's not linearly, but in a constant rate of improvement. This is during the first 3 to 4 minutes. And then it stops, and it doesn't improve for a couple of minutes. And only after between 7 and 10 minutes, and the participant is there, adjusting the intensity of the light. Nothing happens between 4 minutes and 7, 8 minutes. The sensitivity doesn't, and suddenly after 7 to 10 minutes, again, the sensitivity starts to improve. And the participant every time needs a dimmer light to perceive it. What happened? What happened is that, as I said before, you remember I said that reuptake of the cones is much faster. It's 6 minutes and the rods 30 minutes. So what we had is that in the beginning, the cones start to recharge, and because it's dark, the more and more cones become available, which means the more and more cones. I said in the periphery, it can be also in the fovea because it's cones here, but it starts to, it cannot be far away from the periphery, let's say a little bit, where we have both cones and rods. So the cones start to become, more and more cones become available, so the participant is more and more sensible until the maximum cone sensitivity is reached, because we have a maximum amount of cones in our retina. In the meantime, the rods started to recharge here. But because they take 30 minutes each, it's much slower, and until this point, they make no difference. At this point, so here we have these 7 minutes that nothing happened, and then suddenly the rods become more and more available, and then again we have more photoreceptors available to perceive that dim light, and increase until its maximum after 20 something, half an hour, I don't know. Some points some interesting things I want to tell you about dark adaptation. I told you, and I told you in the first that I was in the army, I was in a combat unit. For respect of the entire situation, but I can sometimes talk about technical stuff. So one of the things that we learn in the army when we go out in missions, usually it's at night. We do two things. First of all, from the moment we are some half an hour, sometimes more, from the point we want to be ready for action or whatever, we cover one eye. So we look like, so soldiers look like pirates. We cover one eye, so one eye starts to dark adapt much before we need it. So when we reach there half an hour later, we have, so until then we have one eye that we can use, and when we reach there we have one eye that is already ready to action. Another thing that we do in the dark, when we don't use night vision goggles, night vision are a problem, because if you put night vision, you you destroy your dark adaptation. So there are many night vision devices that are used only in one eye for that reason. But in many situations, we cannot use they. I'm not with them anymore. Soldiers cannot use night vision because if you take it off, you don't see nothing. So this one. The other thing that in the army, maybe you've seen in movies, at night you need light to read maps. For any source of light, we cover it with the red cellophane. What's the name in English? Cellophane, like a plastic. Yeah. So with a red cellophane. Why? Because rods cannot see red light. Rods can see something between this blue and green light, but red light is the furthest from exactly. Thank you, Charles. So this is the further away from the wavelength sensitivity of rods, which is assumed that the enemies, the people that you don't want them to see you, are also in the dark, so they are using their rods, so red light they will not see. Another thing that soldiers do in the dark is when you want to look at something, you don't look directly at that something, because if you are scanning an area, everything is dark. If you look directly at that something, you are using your fovea, you are using your cones that have very high resolution but very low sensitivity to light. So you simply will not see details, you will not see movement. So what we do, and it becomes automatic at a certain point in the dark, until today when I'm in the dark I do it, is that you look around. You fix around. If I want to look at this area, you fixate your fovea around. So the area of interest falls on your periphery, on your rods, which are much more sensitive to very little light. It's black and white. You've seen black and white. And the resolution is not good, but you can perceive, and probably this is the most important piece of information that a soldier wants to attend to, is movement. So I didn't have time to explain to you today, but the same the fact that rods and cones, they converge differently to ganglion cells, they also are much more attuned to movement than the fovea, than the center of our eye. So, and this, after all I said against evolution, but still I have to say what I didn't agree, that animals in a natural habitat are very worried about being eaten. Let's put it this way. So the amount of sensitivity that an animal wants, let's put it this way, the animals that their sensitivity increase in the peripheral area, they survive better. So this same mechanism, this same distribution and convergence, the relationship between the amount of rods to one ganglion cell and cones, also allows for a much better sensitivity to movement. Something that moves on the visual field, the peripheral vision perceives faster. Smaller movements, etc. Okay. All right, where were we? That's exactly what I just said. This is our brain. So these are the optic nerves from the eye, from the ganglion cells. There is the chiasm in the center. They go through a lot of stuff, a lot of story about it that is not part of this course. And then the area of the brain where everything is processed, interpreted deeply is our occipital area, which is the back of our brain here. So it's accepted to describe two different pathways from the moment it arrives to the occipital lobe. These patterns of activations, so information, I don't like this word because again, it's not information, but these patterns, specific patterns, a long time of activation, they follow two, this is simplistic, but two streams, the dorsal and the ventral. The dorsal is usually where things are, is movement, is less resolution, is more connected to survival, to perceiving movement, to perceiving positions. And then we have the ventral pathway, which again, simplistically saying, is a deeper, more calculations through which we end up perceiving what? Identities, associations, even access to consciousness is usually connected more to the ventral than to the dorsal system. One thing I want to say, okay, this is important. So this is the optic chiasm, meaning both sides of each retina, they are combined together into one bundle that reaches the same size of the brain, of the two hemispheres. So you know that most of our afferent information it crosses, right? Is contralateral. So when these neurons from my left leg, they reach my right hemisphere, for most of the body, apart from parts of the faces and the two sides of the two retinas. So it's not left eye, right eye, is right side of both eyes. They are ipsilateral, they go to the same side, and both left sides of both eyes go to the left side, to the to V1, in the occipital lobe, the primary visual, we have V1, V2, V3. So what I wanted to say, and this is important, that our visual system, I still have, how much time do I have? I'm beyond time. Okay, last words. Our visual system is organized retinotopically, meaning that our receptors, by technical, they are organized according to the light that reaches us. So something here and here maintains the geographical relation when it reaches the retina, right? And then it goes through the ventral pathway, and it maintains that geographical interrelationship between areas also in our visual, in our brain. So here you can see this is V1, and so neighboring areas here, they correspond to neighboring areas in our retina. Here we can see in another way. And the last thing that I want to tell you is like this. Every neuron in different areas have a different, they receive information from a different size of area in our retina. So the first V1 receives information from a very small area in the retina. The further away we go, the larger the area, meaning less resolution, much less resolution. This area here, look at the difference, is somewhere in the temporal lobe here, receives information from half of the retina. So it's very sensitive, but very low resolution. My friends, we will continue next time. We'll go deeper into the story about sparseness and distributed representations. And from this moment, we are in our office hours.